Ladies and gentlemen, 6.3 day 2, vectors in the plane. We're going to be solving problems using vectors. Hey, there's the assignment, in case I just don't forget where we saw it. Alright, so we're going to be finding vectors in component form using various information. For instance, here we have the magnitude and angle theta with a positive x-axis. And one thing real quick about the basic entire lesson from this point on, any angle theta we're talking about is always going to be with the positive x-axis. So basically we're measuring it the way we measured angles as we were doing all the regular trig stuff from before, so hopefully it won't be too terribly new or anything shocking. Alright, so anyway, so I've got the magnitude of vector v, which is 8 root 3, and then I've got my angle theta, which is 120 degrees. Okay, well of course 120 degrees is something about like that, so there's 120 degrees. Of course this is a full 180, so basically at this point what I have is a really messy triangle, but I've got 60 degrees left over. Okay, and the magnitude, again, is the length of the vector, so basically, I'll just kind of darken this guy in right here. This is my vector v, and that guy has a length of 8 root 3. Okay, well, hopefully that 60 degree angle kind of cue something in your head that I've got myself a 30, 60, 90 triangle here. So again, there's my 30, there's my 60. Of course, if I draw straight down, I can get a 90 right there. And basically from there, all I have to do is, okay, do my 30, 60, 90 stuff. Again, the 8 root 3 is my hypotenuse, so to get to my short side, I have to divide by 2. So this becomes 4 root 3, although notice, since I'm going in the negative direction, that's actually negative 4 root 3. Okay, and then again, to get from the short side up to the longer leg, I have to multiply by root 3, and if I have 4 root 3 times root 3, that becomes actually 4 times 3, so this actually ends up being 12 up there. Okay. And it is positive 12 because it's going up. Okay, so basically what that tells me now is my vector v, again, my components are simply the x and the y values. Alright, so we got negative 4 root 3 as my x, and then in the y direction, it goes up 12. So basically by having a nice angle and using your appropriate triangle ratios, you can get the component form fairly nicely given an angle and a magnitude. Alright, now let's suppose, again, same basic directions, we want the magnitude, or sorry, the component form of the vector, which is the sum of the two vectors u and v here. Okay, now I've kind of purposely drawn kind of convenient axes for the information I've been given here. But let's see, I've got magnitude of u is 4, and the theta for angle u, that's what that means, is 60 degrees. Okay, so basically, I've got u over here. Basically, this is going to be my u diagram. This is my v diagram, in case that wasn't clear. I've got a 60 degree angle right there with my vector, which is a magnitude of 4. And again, just kind of tearing that apart using my appropriate ratios. Hypotenuse is 4. That gives me a side of 2 down here. That gives me 2 root 3. So basically, my vector u, component form, is going to be 2 comma 2 root 3. Okay, notice a little positive because we're here in the first quadrant. Okay, now my vector v has got a magnitude of 7. His angle with the positive x-axis is 180 degrees. Well, that means 180 degrees is the full, flip it backwards sort of thing. So basically my vector v is going straight this way, a distance of 7. Okay, now granted this isn't really a triangle, but v I can think of the components because I went left 7, so again this is really like a negative 7. So it's negative 7, and then since I'm not either up or down from the x-axis, it's simply 0 right there. Okay, so now I have the component forms of the two guys individually. So then basically just to do u plus v, okay, I just have to have u, which is 2 comma 2 root 3, sloppy, plus the other stuff that we have, negative 7 comma 0. Okay, which again, we just add the x's and add the y's appropriately, so 2 plus negative 7 is going to be negative 5. And then the 2 root 3 plus 0 is a nice clean 2 root 3. Alright, so there's the component form of the sum. Again, basically what we did in that previous example, you just have to do it twice and then add the results together. Alright, it's possible you need to find the angle between two vectors at some point, and there's a set of problems here where the book actually in the direction says use the law of cosines. I think that's kind of silly, and mostly because of just the way that they play out when you actually start taking a look at this thing. We'll use the law of cosines later on something, so don't think you're getting away from it completely, but here I basically suggest not doing it because of how things go, and okay, let's do it. Okay, so I've got vector v, which is simply I minus j. Remember, that's going basically saying 1, negative 1, and the the other notation. And likewise, the 2i plus 2j is basically saying 2 comma 2. Alright, so whatever works for you. But anyway, v is I minus j. So again, that's 1 in the positive direction and negative 1 in the negative direction. Or negative 1 in the vertical. So there you go. There's what v looks like. Okay. And then w looks like 2, 2. So 2 to the right and 2 up. So my vector w looks something like that. Alright. And hopefully it's not too hard to imagine here that if I've got 2, 2, I've got myself a 45, 45, 90. So I've got 45 degrees tucked right in here between the x-axis and where w is sitting. Okay, likewise with v, since I'm going over 1 and then down 1, I've got kind of the same arrangement. 1, 1, and then kind of a root 2, if you will, but that's not important. What's important is it's also a 45, 45, 90 triangle. So I've got this 45 sitting next to another 45, and if I want the angle between those two guys, it's not too hard to figure out that 45 plus 45 is actually 90 degrees. So the law of cosines here would kind of be overkill. So depending on the angle measure, sometimes it's really blatantly obvious what these things will be. Alright, so there you go for that. Alrighty, so again, as promised, this is why the law of cosines is going to come handy, because of the parallelogram method for adding vectors and actually how we can actually find the angle between the vectors and how this kind of all matches together into some sensical sort of thing. At least I hope it is for you. Alright, here we go. Alright, I'm given two vectors here, vector u, and I know it has a magnitude of 7, but that's all I know about it. Likewise, vector v has a magnitude of 3, and then I do know that the resultant, if I put u plus v together, is going to have a magnitude of 8. Okay, so that's not a ton of information, but here we go. We can actually do a lot of good using some geometry and some trig here. Okay, now I don't know anything about any direction for vector u, so I'm just going to arbitrarily, because again I'm not given any sort of other direction, draw myself an angle u, just going in the positive direction. Again, I don't have any sort of angle measured for him, so there he is. Okay, now I've got my vector v, and I've got the resultant that I need to come up with. So, okay, bear with me for a minute or two here. I apologize, but here it goes. Vector v. Okay, if I wanted to have a resultant of 8, okay, I'm going to do two things that are wrong first to explain why I'm going to do what I'm going to do. Okay, let's just pretend for a second that the resultant, which again means basically just stack them end to end, let's pretend for a second that v goes straight to the right. Okay, well this is a 7 and this is a 3, that means that the total resultant would be a 10 in magnitude, and I only want 8, so basically I'm too big right now. Alright, so instead of that v going right there, what if we took v straight to the left and put v like that? Okay, so then of course 7 to the right and then 3 back to the left gives me a resultant of 4, okay, which again is very small compared to the 8. Alright, so I got 10 to the right, I got 4 to the left, but I want 8. So basically, 8's a lot closer to 10 than it is to 4, so what that means for the placement of my vector v is it needs to go something a little bit to the right in order to obtain the complete resultant of 8. So basically there's v. Here's the trick though. I want the angle between the two vectors, I don't want the angle with the vectors stacked on top of each other. So basically I don't want v to be sitting here, at least for the angle that I want v to be sitting right here. So let me just duplicate what I did here for vector v. And now what I want, I'll just use a theta for lack of anything better, I want that angle right there. Okay? And I want that angle such that my resultant is going to be 8. And the resultant is what I get by going end to end for these two vectors. Okay, but the good news is I can either go u then v, or I can go v then u. Okay. And hopefully now you're getting a little clue as to why I'm calling this the parallelogram method, because by adding it in either direction I can obtain either of those two to get to the resultant vector, and by going both ways with this, actually you notice I draw a parallelogram. Alright, that being said, my resultant is basically the diagonal going from the origin to the end of the two vectors being added together, and there you go. Okay, now what this does for me is it gives me a triangle to work with. Okay, up until now I didn't have a triangle, but what I've got, and if I just kind of pull up the triangle there, something like that is what I've got. Again, my magnitude of u was a 7, the magnitude of v was a 3, and the magnitude of my resultant was an 8. So basically, there's my triangle. And the good news about the law of cosines is if I've got 3 sides, I can figure out an angle. Alright, now back to my diagram. I want theta, which notice isn't an angle in my triangle, but if we kind of pay attention to our geometry and our parallel lines, because v and v are going to be parallel, okay, I can kind of play my corresponding angles game, and I get theta right there. Okay, so again, that doesn't really do me much, but it does give me an angle that's adjacent to an angle in my triangle. So basically, if I figure out this angle right here, let's just call him x for the sake of argument, and kind of extend this right here, and there's theta. Okay, by figuring out theta, or in order to figure out theta, basically what I can do is find x, and then notice these two guys are supplement. So basically the theta that I want is actually going to be 180 minus that x value that I find there. And so basically, long story, longer, that's what we're going to have to do to figure out the angle between two vectors if we're given this kind of information. Hopefully that made a little bit of sense. Alrighty, let's put that thought process to work with a kind of a real-world-ish sort of problem. Okay, this is from the world of physics. Okay, so if you're taking physics right now, or have taken physics, a lot of what we do with these vectors is going to make more sense than maybe somebody who hasn't, and my apologies to those of you who haven't taken physics yet, but here it is. Alright, so we've got two forces, one of which has got a force of 80 pounds, which is a magnitude, and force 2 has got 100 pounds of magnitude, and the resultant is 150. Okay, so again, the angle between those two forces is going to be generate that is what we need to figure out. Okay, and again, without any sort of good directions, I'm just going to arbitrarily take my first one, force 1 being 80 pounds, so I'll draw something that looks kind of 80-ish. And it's force 1, so if you want to label that F1 or whatever works for you is great. And then force 2 is 100. Let's change colors just because we can. But again, I want my resultant to be 150, so I'm kind of in that same quadrant again. If I go 100 this way, okay, I'm going to have a resultant of 180. And I want 150, so it's a little bit less. So again, basically what I'm going to do is I'll put the 100 one something about like that. So there's my 100, and again, that's force 2. And you can imagine that guy transposed over to here, but again, I'm not going to muddy up my diagram here. And I'm drawing my resultant. So R for resultant, and that's 150. So again, there's my triangle. And again, theta basically ends up being this. This is the angle between the two vectors. Because again, basically think of sliding the green guy all the way back to the origin to the left, and you can see that angle there. Okay, so again, what I want to find out is x right there. And if I can figure out x, then theta is simply going to be 180 minus the x value. Okay, that being said, if I want to find angle x, using the law of cosines, I want to start with the 150. So I've got 150 squared equals the other two sides squared, 80 squared plus 100 squared, minus 2 times those guys again, 80 and 100, and then the cosine of, well, our angle x. Okay, I'm going to skip a little bit of work here, but basically if I square all three of these numbers and subtract the 6,400 and the 10,000 off of both sides, I'll eventually get a 6,100 equals negative 16,000 cosine x. Okay, dividing off the 16,000 gives me cosine x equals a negative 0.38125, which actually comes out clean that way, it's just a long decimal. And then doing the inverse cosine from both sides gives me x equals something around 112.411 decimals forever. Okay, and again, this is in terms of degrees at this point. Okay, so again, now the theta I want is actually 180 minus that x, and in this case that works out to be approximately 67.6 degrees. So that'll be the angle necessary to generate a resultant of 150 based on those other two vectors. And that's how the law of cosines comes into play for us. Alright, so let's talk another type of word problem. Okay, so for those of you, again, in physics, when you're talking about projectile motion, one very important thing is breaking velocity into horizontal and vertical components, and that's, again, a great thing that vectors can do for us. Okay, so let's pretend we've got some gun firing, and he's got a muzzle velocity of 1,200 feet per second, and it's fired at an angle of 6 degrees in the horizontal. So, without too much here, and I am going to not draw this to scale because otherwise it'd be kind of crazy, but here we go. So here's my vector v, if you will, or whatever, but I've got a velocity vector here of 1200 feet per second. Okay, and basically what I want to know is the horizontal component, we call that v sub x, and I want to know my vertical component, which is v sub y. Alright, so given I want the horizontal and the vertical, I can basically just draw those two horizontal and vertical components in as their own little individual vectors. And okay, notice I put a right angle between them because that's exactly what it's going to be. And one thing I forgot to label was our 6-degree angle. So there's our 6 degrees. Okay, again, very, very much not to scale. But, okay, what's nice about this is I've got a right angle, so SOHCAHTOA trig comes into play. Alright, so in order to get v sub x, our vertical component, sorry, horizontal component, basically all I need to do is set up my standard SOHCAHTOA equation, so cosine of 6 degrees, and it's going to equal v sub x over 1200. Okay, and a little bit of solving should quickly get you to v sub x is approximately equal to 1193 feet per second. So this guy is moving horizontally at 1193 feet per second. Hopefully that makes sense, because if the total velocity is 1200 feet per second and I'm only going at 60 degrees, most of it is going horizontally. So that number being close to this one is not too shocking. To get the y component, which again, if it's only 6 degrees, you can imagine that the y should be relatively small in comparison. And again, SOHCAHTOA gets me sine of 6 degrees equals the y component over that same 1200. And a little bit of calculator button pushing and whatnot gets me v sub y is approximately 125 feet per second. Again, notably smaller than the original 1200. So once I've got that, again, those of you in physics know that I can figure out exactly how far this guy goes and how long it's in the air and all kinds of other good information like that. Now, let's take a look at something where 3 forces are at play. Alright, so I've got 3 forces with magnitudes of 70 newtons, 40 newtons, and 60 newtons acting on an object at angles of 30 degrees, 45 degrees, and 135 degrees. Pardon, a little grease in this here. Degrees. Okay, find the direction and magnitude of the result of these forces. Okay, so let's just take them one at a time. I skipped the word respectively, but the 70 newtons goes with the negative 30, the 40 goes with the 45, and the 60 goes with the 135. Okay, so that wasn't obvious. Okay, so let's just draw them individually and kind of take it from there. Okay, so my 70 newtons, notice the 70 is the largest of the 3, so I'm going to draw him a little bit bigger than the other 2, just to have a vague scale going. Alright, so I'm doing 70, but I'm an angle of negative 30, so basically 30 degrees in a downward direction. He's going to be a 70-ish sort of guy. Okay, so again, if this is a 30 right here, okay, again, finishing off a right triangle sort of thing based on that vector. Okay, if he's 70, again, that gives me a negative 35, again, negative because it's in a downward direction. And then, okay, I'm going to be careful here because I'm going to have some other stuff in the first quadrant. Okay, of course, 35 with a 36 to 90 is going to give me a 35 root 3 as the horizontal part of this guy. Okay, switching colors here. Okay, my 40 newton is the smallest of the 3, and he's got an angle of 45 degrees. So if that's 70, 45 is going to be a little bit shorter. Not quite half as short, but it looks like about 45 right there. Alright, so anyway, there's not 45 degrees, 45 degrees right there, and that's 40 newtons. Okay, nobody noticed that. Okay, alright, so again, the good news about having a 45 is 45, 45, 90 triangles are very nice. Dividing by root 2 gives me a 20 root 2 for that component. It's positive. And again, this one down here that I'm going to have a hard time getting to is going to be 20 root 2. Okay, switching colors for the third time. We've got a 60 newton, which again is going to be very close to the 70 as far as length, is at a 135. Now, 135 is 45 degrees off of the 180. So basically what that does for us here is it gives me a 60, and I'm going to try to draw this a little bit to scale. Again, there's a 45 degree angle, and it's not a very good looking triangle, but hopefully you get the idea. There's my 60 force, and again, if that's a 60, I'm going to get a 30 root 2 in a vertical direction, and then a negative 30 root 2 horizontally, again using one of those good geometry triangles. Okay, so basically there's a picture of all 3 of our forces acting at the same time on this one object right down there that's sitting at the origin. Okay, so the question is, what's the direction and magnitude of the resultant of these guys? Well, in order to do that, the resultant basically just means, again, the sum. So what I need to know is the component form of all of our vectors. So vector 1 is our 70, and his components are 35 root 3 and negative 35. Okay, vector 2 is our 40 in green, and his components are both 20 root 2's. So 20 root 2 and 20 root 2. Okay, finally, okay, vector 3 okay, is a negative 30 root 2, and then a positive 30 root 2. Okay, so once we've gotten that far, basically we can go ahead, and I'm not going to try to draw it into this point because sometimes it's pretty hard to do. Although if you're good, you can kind of get a vague idea where this guy's going to go. So our resultant vector, component-wise, is just adding all three of these things together. If I do so, adding all of my x's together gives me 35 root 3 minus 10 root 2 is the x component, comma. Doing the same thing with y's gives me a negative 35 plus 50 root 2. Now, admittedly, that doesn't do us a lot of good. So I think in this case, converting this guy into decimals is probably convenient, at least for drawing what this guy is going to look like. So our resultant vector decimal form is going to be 46.47 and some messy decimals, comma 35.71 messy decimals. Okay, basically what that does for us now is we can at least visualize this guy a little bit better, thinking of these guys at least in a rounded form. But we're not done with the problem yet. All we've done is got the component form. We're still going to need to figure out the direction and magnitude, and for that we're going to go to our next slide. Okay, now again, the good news of having this resultant in decimal form is I can draw myself a reasonable representation of it. Okay, so in the x direction I'm going kind of 46-ish, and in the y direction I'm going 35, almost 36-ish. Okay, so horizontal component is 46.47, dot, dot, dot. And again, notice that the, oh my gosh, that's horrible right there. The 35 is smaller than the 46, so I'll try to draw him a little bit smaller. 35.71, dot, dot, dot. Okay, so going to nice big red color here. Basically, this is my resultant vector right there. So these are as we think. Alright, so once we got this far though, the angle and the magnitude aren't too really tough to come up with. And you can actually do either one, it doesn't really matter the order. So for the sake of argument, let's do magnitude first. So the magnitude of our vector right there is, again, magnitude's kind of nice, it's just basically the Pythagorean theorem. So we got to take my 46.47 d decimal. And one thing I probably could have mentioned earlier is a very good idea to save that in your calculator's memory if you don't have Inspire. 35.71 dot 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 squared. Okay, punching the buttons on that gives me approximately a 58.6 Newton magnitude for my vector resultant. Alright, so there's one of my two answers. The other one is I need the direction. Well, again, the direction is the angle off of the positive x-axis. And again, since this one's nicely in the first quadrant, we can directly find the theta here and we're good. So that the two that I have here, and admittedly now that I have the third side, I could actually use any of the three SOHCAHTOA trig functions, but I'll just go with the two that I've got on my diagram, and that tells me that I'm going to have to do the tangent of theta equals opposite over adjacent, so 35.71 dot 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 over 46.47 dot dot dot. Again, you got to use all those decimals. Trig is a little bit touchy, throw things off. So basically now I'm doing the inverse tangent of that icky fraction. Should give me a theta value that I can work with. And again, before I even press equal in my calculator, if I notice this is 46, now that's 35, okay, notice the horizontal is bigger than the vertical, so I know I'm looking at an angle less than 45. So if something bigger than 45 comes on my calculator, I should go, oh, wait a minute, and see if I've done something wrong. Okay, but basically, after putting those buttons in my calculator, I should get a 37 approximately 0.5 degree angle. And there we go. Okay, it didn't happen here, but let's say this was in the second quadrant or something like that. If it was a second quadrant angle, I'd have to subtract it off of 180 or something like that to get my actual angle for the vector. But there you go. Okay, again, hopefully that all made sense. Of course, anything that didn't, please ask me in class. Make sure you make good decisions and choose wisely.